So welcome back. We are now finishing week number 10 for Math 140 Business. This is November 4th, and we are going to do today chapter 19 on the sampling distribution for a mean. Sampling distribution for a mean. And we've talked about this before, the concepts in this chapter. Do you recall that applet? Remember that applet that we went through some time ago with the different graphs and what happens if the sample size increases and the shape of the graph, shape of the distribution changes? Do you recall that one?
Yeah.
So the applet was called the central limit theorem applet. And now in this chapter, we're finally going to learn what the central limit theorem says. But we're going to start with one of the most important laws in all of statistics is called the law of large numbers. And there's a few laws that are just like significantly more important than all others, and this is one of them. It says draw observations at random from any population with mean mu as the number of observations increases, the mean X bar of the observed values, not the mean of the underlying population, but the mean of the observed values, gets closer and closer to what?
The actual mean?
The actual mean, which is mu. So if I flip a coin one time, is it more likely to be heads or tails? Assuming it's a fair coin.
Equally likely.
Equally likely, right? Fair coin, 50-50. If I flip a coin 100 times, does that mean that it's just as likely to be heads no times as it is to be heads 10 times or 20 times or 50 times or 60 times or 80 times? Is the fact that each flip is 50-50 going to make it that if I do 100 flips, every possible outcome is as equally likely as any other possible outcome? What do you expect to happen if I flip a coin 100 times, a fair coin? How many heads would you expect to see if I flip a coin 100 times? What vicinity of an answer would you expect to see if I flip the coin 100 times?
Somewhere near 50.
Somewhere near 50. Would you be shocked if the answer was 40? No, 40 is not too far away from 50. I don't know if I'd be shocked. I might be a little surprised, but it wouldn't like make me rethink everything that I believe about the universe. But if I flip a coin 10 times and I got 2 heads, would that be crazy unlikely?
Depends on the order.
Sorry, depends on what?
On the order. Like let's say you get it the first 2 and then the rest are
Yeah, well, I don't even care about the order. I flip 10 coins at once and they all fall and I look at them and I count 2 heads.
I don't think it would shock me like that much just because 10 is like not that significant of a value.
Exactly. But when it gets to 100 or 1,000 or 1,000,000 or 1 billion, If it
Yeah.
remains 20%, I think you'd be more and more a little surprised, right?
That's not a fair coin.
And that would be my conclusion, right? I would reject the null hypothesis that it's fair, and I would say it's probably not fair. But this is exactly what the law of large numbers says. That for small values, yeah, we have no idea what's going to happen for small values. But as the number of observations increases, the average of my observed values is going to get closer and closer to the true value. So 20% from 50%, it's kind of far away for 10 flips. For 100 flips, it would be even more surprising. For 1,000 flips, even more surprising. For 1,000,000 flips, even more surprising. Because as the number of flips increases, I really expect the value to get closer and closer to 50%. So to be far away from 50% for large values would be a little surprising. Does that make sense?
Yes.
So this is the law of large numbers. In general, you have two things. You have a population and you have a sample. The mean of the population is mu. The mean of the sample is x bar. It's my sample mean. What is the standard deviation of my population? It's sigma. And what is the standard deviation of my sample? It's S, correct? The sample standard deviation, correct?
Correct.
Now, if I took lots of samples, if you drew many samples, each of the same size, n. So let's think about this for a second. Suppose you have a population, some mean, some standard deviation. If I take a sample from this population, will I get the same average every single time?
No.
Probably not, right? Unless I'm really lucky. Chances are I wouldn't get exactly the same result every time. Would I get the same standard deviation every time?
No.
Probably not. Which means that x bar itself and S each have their own, oh, not Dave, that's my name, each have their own distributions. Because remember what a distribution is. It's different possible values together with your likelihoods. X bar is something that I do not know in advance what it's going to be. S is something that I don't know in advance what it's going to be, which means it itself has a distribution. As such, X bar has a mean and a standard deviation as well. What is the mean of X bar? If you take lots and lots of samples, each one of which from a population whose mean is mu, what do you think the average of your averages is going to be?
Would it be mu?
It would be mu itself. The mean of X bar is the same as the underlying mean of the population. But a better question is, what is the standard deviation of X bar? And here we want to use the law of large numbers. The law of large numbers says, as the sample size increases, we hone in on the true value, correct? Right, that's what the law of large numbers says?
Yes.
Which means, what should happen to the spread of my data as the sample size increases? If I hone in on the true value, that spread should get smaller as the sample size increases, so that I'm more likely to be near the true value, right?
Yes.
So it turns out, without doing the math, I just have to give this to you because unfortunately in statistics, there are so many things that it would be awesome to prove that you guys just as a whole are not ready for. But it turns out that the standard deviation of X bar is the underlying sigma, the underlying standard deviation of the population, but we divide by the square root of n. So that as n increases, the spread decreases and I hone in on the true value. And no problem, Michelle. I'm just going to mark you here. Glad that you can join us. But again, not proving anything to you, just giving you facts that we can work with to solve problems. So if the original X, not X bar, the original X is normal with mean mu and standard deviation sigma, i.e. X is normal with mu sigma, then X bar is also, well, is also normal with mean mu and standard deviation sigma over the square root of n, i.e. X bar is normal mu sigma over the square root of n. And the question is, great, this is wonderful information, but how exactly does this, is this useful in practice? So before we move on, are there any questions with what I've done so far? Again, recognizing the fact that some things you got to take for granted, I can't prove them.
Wait, that says X, and then what does the squiggle represent?
Has the following distribution. It's like a shorthand notation for saying X is normal with this mean and this standard deviation.
Okay, thank you.
Okay, it's a shorthand notation. So let's do a following example. It says during World War II, 12,000 able-bodied male undergraduates at the University of Illinois participated in required physical training. 12,000, that's a lot. That's probably my sample size. Let's call it N for now. And as we'll read through the problem, maybe it'll turn out not to be N, I don't know. But for now, let's call it N. Each student ran a timed mile. Their times followed the normal distribution. So the time, capital T, is normal with a mean of 7.11 minutes and a standard deviation of 0.74 minutes. As I read through the rest of the problem, I realize that N equals 12,000 is not the sample size. That's actually the population. So we'll call that capital N. What we have now is an SRS of lowercase n equals 100 students. Had a mean time of 7.15 minutes. And a second SRS of n equals 100 students had a mean time of 6.97 minutes. These are just facts. After lots and lots and lots of SRSs of 100 were taken, we saw that T bar, we'll call it X bar. So capital X bar was normal with a mean of 7.11. And what was the standard deviation for X bar?
1?
Not 1.
0?
Well, if the standard deviation was 0, that means there's no spread. If there's no spread, then they should all be the same results. And we see here we got two different results. Right? So it can't be 1, it can't be 0. What is the standard deviation of X bar? And I guess we'll go back and call this, instead of calling it t, we'll just call it x like the rest of the problem. What's the standard deviation of x bar?
Would it be 0.74 divided by the square root of n?
And what is n?
100?
So what do we get?
Won't you get 0.074?
Yes. So x bar equals 7 is normal with a mean of 7.11 and a deviation of 0.074. So here's the question. What is the probability that a single person ran a mile in, let's say, more than, I don't know, let's say 8 minutes? What's the probability that a single person ran a mile in this study in more than 8 minutes?
Can we do normal CDF?
You better. That's what I just did.
So 8 would be the lowest, and we put on the upper like 9999, and then mean is 7.11, standard deviation 0.74.
What do we get?
I'm gonna put it on my calculator.
It was 1.32 and then e to the negative 33.
Wow. Did you do it with 0.074 or 0.74 your standard deviation? Because we're doing one student now. We're not doing a sample.
I got 0.11454.
Yeah, that's what I get. 11.5%.
Yeah, there you go.
Do we all agree on this? Those who bothered to try?
Wait, so we use 0.74?
Yes, because we're looking at one person. We're not looking at a sample. We're looking at one person from the original population. The population had a mean of 7.11 and a deviation of 0.74. So the question is, what's the probability that one person was more than 8? And the answer from the calculator is about 11.5%. We agree?
I got a
Yeah.
negative.
You got what?
I got a negative 11.5.
Did you go from 8 to infinity or negative infinity to 8?
Oh, negative. Oh, I don't.
What do you do from where to where?
Let me. I did from. Oh wait, it's okay.
So you're with me? Or you're not with me?
No, can you just go over it one more time?
Yeah. So on your calculator, lower is 8, upper is 9999, whatever. Mu is 7.11. Sigma is.
Are you doing normal CDF?
Yep, normal CDF. That's what this N stands for, right? It's normal.
Yeah. Okay.
So you're with me?
So what's your upper?
Infinity.
Oh, okay, that makes sense.
Greater than 8, right? 8 and up.
Oh, okay. That makes more sense. All right, thank you.
So let's do a question. If you took someone at random and they ran a mile in more than 8 minutes, would you be completely shocked?
No.
No. 11.5%. Certainly I wouldn't expect it, but it wouldn't be crazy if it happens. What's the probability that X bar is greater than 8? That I took 100 people and averaged them, and their average was greater than 8. What's the likelihood that that happens?
Don't we just change the standard deviation to 0.074?
So that was what I got earlier. Or?
Yeah, that's 1.32 times 10 to the negative 33 power. Essentially, it's 0. It's impossible. Because for one person to score more than 8, at the end of the world, 8's about here, right? So look at all that likelihood that they scored more than 8, correct? Lots of room. But for 100 people, to have an average more than 8, and of course, this is not to scale here. If I try to do it to scale, it'll be more like, well, let's try to do it to scale. Even that's not the scale. But for 100 people, the standard deviation has decreased by a factor of 10, which means it's much skinnier. Actually, it should go much higher too, because it's much skinnier, so it has to go higher to compensate.
Wait, why are you doing 10 to the negative 33 again?
Well, that's what the calculator gave me. I didn't want to do it, but the calculator gave me 1.32 times 10 to the negative 33 power.
Oh, okay.
Right? The likelihood of being past 8 when the sample size increases to 100 is so small because my curve is squeezed in by the law of large numbers. And therefore, the likelihood of the average being more than 8 is negligible. Because think about it. 10% of people are past 8, correct? 11.5% of people individually are past 8, right? For me to take 100 people and have their average be past 8 would mean that more than 50 of them are past 8. How likely is it if I take 100 people, each one individually of having an 11.5% chance of being past 8, that 50 of them will be past 8?
It's pretty unlikely.
It's negligible. That's the whole idea of taking samples, is when you change the deviation so to make it smaller, rare outcomes become even more rare. This is the whole idea of the law of large numbers. This is it. Does that make sense?
Yes.
Okay, so now we finally have the central limit theorem, which I have mentioned in the past, that applet that I did a few times a few weeks ago, that shows that everything eventually looks normal. That is the central limit theorem. And it says draw an SRS of size n from a population with mean mu and standard deviation sigma. X bar is approximately normal. X bar is approximately normal if n is large enough. Note, if X was already normal, X bar is automatically normal. This is the central limit theorem. And we saw that applet. And we saw, when we went to the applet, it's been a few weeks, but you guys remember how large of a sample was necessary before even very strange looking distributions look normal?
I think it was around 8, wasn't it? Or
yeah, it didn't require a huge number, right? Even by 6, 7, 8, some of these things were looking normal already. So usually a good rule of thumb is, to have it be 30 or more. But as we saw, even for 10, it can look normal. So if you're ever out there in the world and you have to worry about using the central limit theorem to make sure that it's normal, you might want to make sure of it if you're going to have a smaller sample size. But once you hit 30 or so, usually you're good to go. Some books that I've seen use 40, but but certainly by 40, you can assume it's normal. And because it's normal, I can use a normal CDF. See, if it's not normal, I can't use normal CDF. Can you scroll up a bit? This way?
No, I went the other way.
Oh,
Thank
but I didn't. Okay, no problem. So let's do an example. Another example to illustrate this. So it says the time in hours that a technician requires to perform preventive maintenance on an air conditioning unit is governed by the exponential distribution, whose curve appears like this. This is the exponential distribution. It is most certainly not normal looking. That is the exponential distribution. It has a very high likelihood for small numbers and a very small likelihood for larger numbers. By no stretch of the imagination does this look like a normal curve. In fact, if we okay, this number 8, this is the exponential distribution. So if I go to 5, what do you think? Would you think that's about normal?
Yeah.
Yes or was that a nah or a yeah?
I think a normal doesn't necessarily have to be in the middle, right?
No. Well, what's the middle? I mean, every normal has a peak, and it's symmetric on both sides of the peak, but it doesn't have to be the normal middle of the picture, right?
Then yeah, that's about normal.
Yeah. So even by 5, if we go to 4, well, it still looks right skewed a little bit. That right skewness is a little concerning. How far do I got to go before the right skewness goes away? Let's see, by 10, by 15.
That's pretty even.
Yeah, I mean, yeah, we're pretty much there. It's pretty negligible already. By 20, certainly. So but one thing you'll notice, by the way, what's the mean of this one that we just did? It says mean equals 24.3, right?
Yes.
If we go to just 1 again, what's the mean for this one?
24.3.
Because that is the first thing we did today, right? The mean of the sampling distribution is equal to the mean of the underlying distribution. The deviation gets smaller, but the mean stays the same. So we have this exponential distribution. We're given that the mu is 1 hour with a standard deviation that's also 1 hour. It's actually you don't need to know this for this course at all, but it's an interesting piece of information that the mean and sigma for the exponential are always equal. Now, your company has a contract to maintain 70 of these units. So these numbers are for each unit. Each unit, to repair each unit or to make sure each unit is running properly, requires on the average 1 hour of time with a standard deviation of 1 hour. And you need to check 70 units. That's your job, 70 units. So how many hours should you schedule to check these 70 units? Right? You're the boss. You're scheduling your technician. You don't want to say, hey, go there for a month, you'll be fine. Because he doesn't need a month. Worst case scenario, it's not going to be more than, 500 hours. Doesn't need a month. But he needs more than a few hours, right? So how much time should you schedule? In particular, is it safe to budget 1.1 hours per unit? Is it safe to budget 1.1 hours per unit? Or should you budget 1.25 hours per unit? That's the question. Is it safe to budget 1.1 hours per unit, or should you budget 1.25 hours per unit? So, who here has an idea for how to attack this problem?
We can use the normal CDF and then put 1.1 as the lower, and then see how much percentage it might be higher. Like,
well, how can I use the normal if this is an exponential?
Is the mu and the standard deviation for each unit?
Yeah, this is for each unit. Each unit, X, is exponential.
There's 78 units, isn't there?
Yeah, and therefore?
You have enough of, you have enough to have an X mean that's going to be normal?
Fantastic. Even though each one individually is not normal, but X bar, the average of them, is normal, or at least approximately normal. 70 is enough that we can use normal CDF and get a result that's in ballpark. What would the mean be for the average of 70 units? If each unit takes 1 hour on average, then on the average for 70 units, how long should it take?
1 hour.
1 hour, right? The mean is going to be 1 hour. Now, if the standard deviation for 1 unit is 1 hour, then what is the standard deviation for the average of 70 units?
Be 1 divided by square root of 70.
Excellent. So X bar is normal with a mean of 1 and a deviation of 1 over the square root of 70. So the question was, is it safe to budget 1.1 hours per unit? In other words, what's the probability that X bar ends up being more than 1.1? That's the question. How likely is it that it's going to take me more than 1.1 hours per unit? Let's calculate this. How do I calculate this?
Normal CDF.
Normal CDF.
I can already kind of see that it probably wouldn't be, just because the standard deviation is 0.113, and that's it's only 1 deviation.
Right. So let's do the math and see what we get.
Okay.
But you're right. I mean, this is what I'm looking for, what I'm hoping for, is to get to a point where you don't always have to do the math, because you can see what the answer should be.
What do we put as the upper and lower bounds?
Well, greater than 1.1. So what's the lower? What's the upper?
Greater than 1.1. So 1.1 is the lower.
And what's the upper?
No.
Infinity. Yep.
So the percentage would be like 19% of the time.
I didn't get 19. I got close to 19, but a little higher than that. So what do you do for 1 over root 7? Did you do rounds?
Yes.
I actually did 1 divided by square root 70 in the normal CDF.
Oh yeah, I rounded to.
Yeah. So try to be a little more accurate. Literally put in 1 over the square root of 70 there.
Okay. Okay, I got 0.20139.
Yeah. So there's a 20% chance that it will take more than 1.1 hours per unit. Is that something you'd like to risk if you were budgeting for your company?
No.
Oh,
Okay, well, let's take a look if 1.25 hours per unit is any better. What do we get for this one?
Um, 1.8%.
Yeah, 1.8%. Now, is that an acceptable likelihood of, if you were budgeting it for your company, is having a 1.8% chance that you are going to go late acceptable, or would you go even longer?
I think maybe 1.3, but I feel like, maybe like I would do like 1.3 hours per unit, but I think it's like a small enough percentage to the point where I wouldn't really care about it. It's like 2 units, so.
Okay, but you can see how this is a very practical question, because I'm sure you guys have experienced deliveries from Amazon, from, you buy a new couch, you buy this, whatever the case may be. And, you're eighth in line for the day, and, you're waiting at home, and the question is, oh my God, when are they going to arrive? Well, there's variability in every delivery, right? So they're not all going to take the same amount of time. So what do these companies do? They budget a certain amount of time based upon averages, based upon how long on the average deliveries take. And if they budget too much time for each one, then they can only deliver, 10 things in a day versus 15 things in a day, which then backs them up for multiple days. If they don't budget enough time, then they have problems in the other direction. So you can see how this is a very practical question where companies can use this information to actually increase their profits. This is not just very, an abstract statistical idea, but it has very practical applications. Does that make sense?
yeah. I feel like a company would be okay with that just because they're trying to make a profit in a way, and they're trying to cut as much as possible.
Right. So 20%, 1 in 5. Okay. I a little more time than that, even though, 80% of the time you'd be fine, but the other 20%, not so much. 2%, I think even I would be okay with 2%. But the fact of the matter is that, the idea of the original population distribution and the sampling distribution, if it's big enough, it becomes normal. If it becomes normal, we have normal CDF on our calculator. It makes our lives easier. Does that make sense?
Yes. And so how many did you say? It was 30? 30 should be enough, or 40?
Certainly by 40. I've seen some books use 40. I've seen some books say 30. On a case-by-case basis, if I was not actually, if I'm out there in the world, if I had reason to think that even 20 was good enough, I would use 20. It's a case-by-case basis, but certainly by 40, you're going to be fine.
Okay.
Okay. If you were asked a question where it was like, 30, 35, you might want to make a comment and say, assuming that this is large enough that I can use a normal, this central limit theorem, this is what the answer would be. But I certainly want to check to make sure it's okay. Something like that.
Okay.
In general, 30 to 40 is fine. So any questions on what we did here today so far?
No.
Okay, because that was chapter 19. Chapter 19 is now complete. And as such, we are going to start, because we have too much time to leave early today. We're going to do chapter 20 now, or at least start chapter 20. On inference about a population mean. Because all of our confidence intervals and all of our hypothesis testing so far have been about what? They've all been about what? Everything, every one that we've done so far has been about what?
Samples?
Well, not just samples, but what kind of parameter were we always trying to approximate or guess or test? Sorry? Proportions. They've all been proportions. One proportion, large sample. One proportion, small sample. Two proportions if we got that far. I don't recall if we did two proportions or not. Did we do two proportions? I really don't remember what all the details. I have too many classes going. Yeah, we did two proportions. That was chapter 18. Right? So everything's been about proportions so far. And we haven't done a single thing about means, averages. So that's what we're gonna do right now. Although, yeah. Okay, you all with me so far?
Yes.
Okay, so we're gonna start with the simplest case. Confidence interval of about or for a population mean when sigma is known. So this is case one. The confidence interval for a population mean when sigma is known. So you have a population. It has an unknown mu and a known sigma. You might say, well, how do they know sigma? And the answer is, this is a statistics class, so we can make up whatever we want. For whatever reason, they know it. Somehow they know it. And then you have a sample, and the sample has a X bar and an S. It has a sample average and a sample standard deviation. And we would like to use what we got, and of course the sample size n. And we would like to use what we got from our sample to come up with an interval for the unknown mu. So what do you think is the best 1 point guess? If I had to give one number for my guess as to what mu is, what's the best single number I can use from my sample to guess the population mean?
X bar.
X bar, my sample mean. So my confidence interval is going to be X bar plus or minus something. Right? X bar should be right in the center. It's a perfect guess. My sample average. I can't beat my sample average to approximate the actual average. So the question is, what do I add and subtract from that to create my interval? Well, for proportions, what was the first part of the next piece, the margin of error? What do I always start with? X bar or p hat plus or minus what?
Something star, I think.
Yeah, it was Z star.
Star.
Right? And that was either 1.645 or 1.96 or whatever the case may be. Now, for proportions, what was the thing after the Z star?
Was it standard error?
It was a standard error, which was what in the case of proportions? What was it in the case of proportions?
Was it?
Yeah.
I'm looking through my notes trying to find it.
Ah, well, if you're looking through your notes, I'll just give it to you. It was a square root of p hat 1 minus p hat all over n. Does that ring a bell? The square root of p hat 1 minus p hat all over n?
Yeah.
Yeah.
Okay. Well, this one, we don't have a p hat. It's not a proportion. This is a mean. So without going into the proof, and is given to you as fact. And remember, you can use your notes for tests. So you can write down formulas for all of your confidence intervals and all your hypothesis tests. It's X bar plus or minus Z star sigma over the squared of n. That is my confidence interval for the mean when I know sigma.
So this isn't a practical thing in the real world, right? It's just for statistics, or?
You mean because we don't know sigma?
Yeah, is it something that can happen, or?
Yeah, I mean, at a practical standpoint, I don't think I would ever use this because you never truly know sigma.
Okay.
So unless the sample size is really, really big, to the point that I can rely upon it, I probably wouldn't use this.
Okay.
But in statistics class, you can use it. So what about a confidence interval for a population mean when sigma is what? Can anyone guess?
1.
You like that number 1 so much. Unknown.
Oh.
What about the confidence interval for a population mean when sigma is not known? What is wrong with this formula when sigma is not known?
You need sigma?
Well, you can't use it if you don't know sigma, right?
Yes.
So we replace sigma with the next best thing. What's the next best thing if I don't know the actual population standard deviation?
The
sample.
The sample standard deviation. However, because of this extra uncertainty that I have, I don't use Z star. I use something called T star instead. Now, your calculator doesn't care if you're using Z or T. In fact, if you go to your calculator and you look at the confidence intervals, how are they labeled? Go right now, even if we're not going to go to one, go to your confidence intervals in your tests. You see they're all labeled with one of 2 letters. What are the 2 letters that we use for all of them?
Z and T.
Z and T. So up until now, everything has been Z, Z star, Z star, Z star. But if you don't know sigma and you're going to replace it with S, we're going to use T star instead. And the question is, what exactly is the difference between Z star and T star? And essentially the difference is that T star is a little bit wider than Z star. So each T star is a little larger than Z star. So the confidence interval is wider to compensate for the additional uncertainty when we use S instead of sigma. So T star is a little bit larger than Z star. So the confidence interval is a little bit wider. T star depends on the confidence level, of course, like Z star does. But also, what else might T star depend on? It also depends on N, the sample size. As N gets larger, T star approaches Z star. So the larger the sample size is, the less the uncertainty matters, and T star hones in on Z star. Does that make sense?
Yes.
Yes.
So if I go ahead and load up a T table, if I load up a T table, then if you look at, for example, the 95% confidence level, and you can see the confidence level on the bottom of the table, 95% is right at the end of the word level. Do you all see the confidence level, 95%?
Yes.
Right above it, the first line on the bottom is your Z. And what do we see? 1.960, which is expected, correct?
Yes.
Well, as you move up the column, what happens to those numbers?
They get larger.
They get larger. And if you look on the left side of the table, the numbers there get smaller. In other words, working backwards, as the numbers on the left get larger, T star approaches Z star. But they're not labeled on the left by N, the sample size. They're labeled by what? What are those letters that are labeling the numbers on the left?
DF.
DF. DF, which equals the degrees of freedom, is N minus 1. The sample size minus 1. So as I go back to that picture, I can see that at 95% confidence, if N is equal to 10, if the sample size is equal to 10, what would my T star be?
2.228.
Well, 2.228 would be if my degrees of freedom is 10. If the sample size is 10, what's my degrees of freedom?
2.262.
Well, the answer is 9, right? 9 degrees of freedom. And therefore, I go across to 9 and 95%, and I would get a T star of 2.262. Yeah, you can come in.
Do you know what time you start home?
Anytime you want to start, you let me know and I'll leave.
Usually we're like go to after 8:30.
Oh, I'll be done by then.
You know?
Yeah, I'll be done by about 8.
All right.
Probably a little earlier. Okay. All right. Does that make sense so far, everyone?
Yes.
Okay.
Yeah.
So let's do an example both by hands and with the calculator to illustrate this. So okay, here we go. Oh, that's gross. Okay. Body mass index of young women. In an example earlier, we discussed yada, 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 fine. So here we have the following situation. We have an X bar of 26.8, a sample standard deviation of 7.42. We have a 95% confidence. And we have a sample size of 654. And the question is, find for me a confidence interval for mu, for the true value. 95% confidence interval for the true value. So let's go to the formula. It says X bar. Do we know what X bar is?
Yes.
26.8 plus or minus T star. So 95% confidence, N equals 654. What would I use? 95% confidence, N equals 654.
You would Probably like 1.961.
1.961 would be for a sample size bigger than 1,000, right?
Oh, my bad, my bad. I didn't even notice that. I'm sorry.
Okay. So what would I use for this problem? 654, or technically 653, is not on the left. So, yeah.
Oh, are we supposed to like calculate the number, or do you just want us to estimate that based on the values?
Give me an exact number that's the most appropriate to use here.
1.9 1.979 maybe.
Okay, so you kind of took a number in between.
Yeah. But
So-
leaning more towards the 100 than the 62.
So here's what,
I-
no, it's a good guess. And if I did it on my calculator, I wouldn't have to guess. My calculator would give the exact value. But if you're doing it by hand, you always have to err on the side of caution. Since I don't know where between 1.984 and 1.962 I would actually land, I would always make my confidence interval as big as possible and therefore take 1.984, which is a number higher up. Always make it wider rather than smaller. Does that make sense?
yeah.
So my T star here is going to be 1.984. My S is 7.42. And then I have the square root of 654. And when I do that, what do I get? From where to where?
I think I put it wrong, but I got like 0. Yeah. Like 0.5.
Well, you mean for this part here or for the whole thing?
No, for the right part.
For the part on the right? Yeah, I got 0.5
Yeah.
something.
Okay, cool.
Yeah, I got 0.5.
For the interval, I think it would be 26.224 and then 27.376.
Yeah, that's what I got. So the true value, I am 95% confident that it's between those two numbers. Now, let's do it on my calculator, or let's all do it on our calculators. So this is a new one. Which stat test are we going to use here?
Would it be the t-test? Oh,
It's not a test. This is an interval,
well, t-interval.
T interval. So what do we get?
I got 26.23 and 27.37.
Excellent. So we see it's a slightly smaller confidence interval, negligibly smaller, but smaller. Because the calculator knew the value of T star for n equals 654, and we had to kind of round up. But we're talking about being off by, 100th of a, one 100th of a point. Does that make sense? Yes, no questions?
Yes, that makes sense. Sorry.
Yes.
So we'll stop here. We did a chapter and a half. we'll finish 20 and we'll do 21 next time. And then when we come back from the break, because we're off for Thanksgiving, and don't forget, there's a quiz this weekend that I'll put up. We'll spend a day going over lots of problems where I won't tell you if it's a mean or a proportion, or if it's 1, or if it's 2, or if I know sigma, if I don't know sigma, a small sample, large sample. And you'll have to look at the information and decide which case it is, and then take out your calculator and plug it in. It's the most accurate portrayal of what the test is going to be like, where I don't tell you which version it is, and you have to figure that out. But again, it's not hard. 1 sample or 2, that should be obvious. Mean or proportion should be obvious. No sigma, don't know sigma. Large sample, small sample. Okay, maybe not so obvious. But narrowing it down, which one to use, if you understand what's going on to some extent, is not really that difficult. And then plugging into the calculator, it's got to remember what goes where, and then bam, out pops the answer. So all these formulas that we do by hand, it's nice to know where the calculator is getting the answer from, but at the end of the day, let your calculator do all the work. So are there any questions? Going once.
Can I ask a not math related question?
Scorpio.
No, so we have next Thursday off, right?
Yeah.
And then for Thanksgiving, do we just have the 25th off?
We only have that Thursday. We do not have Tuesday. So we have off Thursday of next week and then Thursday of 2 weeks following.
Okay.
But all Tuesdays we're on campus.
Okay. Got it. Thank you. The 30th.
Say again, what?
Midterm is on the 30th.
And the exam's on the 30th. That's correct.
Okay. Thank you.